welcome. Today we have a second lecture on neural networks. In the last class, we had an introduction to the neural network and we discussed linear threshold units or perceptrons, and we looked at how to train neural networks using linear threshold units. The objectives of today's lecture are as follows. The student will learn what are the limitations of single layer perceptron networks. We will introduce multi-layer networks. The student will become familiar with a sigmoid unit and the properties of a neural network unit which uses a sigmoid function. The student will learn how gradient descent works with sigmoid units. Multi-layered neural network with sigmoid units will be introduced. The back propagation algorithm will be described, which is used for training multi-layered neural network. The student will also be exposed to several issues in designing a neural network. For example, selecting the topology or architecture of the neural network and tuning the various parameters so that the network is able to work on a given problem. So, as we have seen in the last class, a neural network is a system which has been inspired biologically. We have a network of simple processing elements which are connected to each other via weighted links. The inputs are fed to the input units, and as a result of the computation done in these units, the outputs are produced. So, just to give an introduction, let us look at some uses or applications of artificial neural networks, which we call ANN. ANNs have been used for recognizing handwritten letters, for predicting online the quality of welding spots, for identifying relevant documents within a corpus, that is a large number of documents, the visualization of high dimensional space, then tracking online the position of robot arms. So, there are many uses that neural networks have been put into. What I just described is just a small sample of few of the utilities of neural networks. So, when you are doing machine learning, usually you will be given some problem and you will have to find out what learning method is appropriate for tackling the problem. In this class, we have looked at a few learning methods, namely the decision trees, as well as now we are looking at neural networks. There are many other learning methods which have been used, but all of these we will not be able to cover in this class. So, normally when you have a real life problem which is posed to you, you have to decide which learning method to apply. You have to guess which learning method will be most appropriate for a given type of problem. Let me briefly tell you what are the types of problems for which the ANN can be considered and appropriate to apply. So, usually problems where we have got a lot of training data, but we do not have a very good model of the data. Those are the problems for which we can apply artificial neural network. So, problems that we cannot mathematically analyze or find a mathematical model to model the problems, but we have enough data. It is using neural networks is a good idea to model such problems. Neural networks also achieve nonlinear multidimensional input-output mapping, where the linear modeling does not work. And also, if we are trying to model a problem with neural network, we have to spend some time in finding the appropriate network and training the neural network. So, even after we have decided to use a neural network, it will take, as we will discuss today, it will take some time to tune the neural network topology as well as parameters, as well as the training of the network. So, some time will be spent in doing that. Neural networks are also able to handle noisy training data very well. Decision trees, the method that we looked at in the earlier class, decision trees are very good for data which is not always noisy. A lot of the data is nominal. When we have some when we require some function to learn a function which humans can interpret and understand, or rules that we can understand. In neural network, when we get a hypothesis, the hypothesis is represented by a set of weight values. So, the rules are not symbolically or understandably present to the human being, human user. So, this is the reason why neural networks methods are often referred to as black box methods, because we cannot interpret easily the rules that neural networks learn. So, just to recapitulate, in the last class we looked at linear threshold units, where we have a sigmoid unit which does a weighted summation of the inputs, followed by a application of a thresholding function or a step function. We also looked at how if we have a function which is continuous and differentiable, we can use gradient descent to find out the set of weights for which the function has minimum error. So, if we have a thresholding unit which is a non-differentiable function, we will not be able to do gradient descent, but if we have simply the linear function, suppose we just have the summation unit and no thresholding unit, in that case we can do gradient descent on the weight surface and try to find the set of weights for which error is minimum. We discussed that linear units or even linear thresholding units are able to classify correctly those instances which are linearly separable. For example, here we have a set of points A and B. The A are the positive examples, B are the negative examples, and we can find a line which separates the A points from the B points. Such problems can be tackled effectively by linear units or linear thresholding units. However, there are problems where the decision boundary is not linear, where a linear decision boundary does not exist. In that case, we will not be able to find a linear decision surface. Suppose we try to find a linear decision surface, we might be able to find some surface, and you will notice that there are some errors. Like we have this, we are trying to separate the green balls from the pink balls. You see, on the right hand side there is one pink ball, on the right hand side there are some green balls. So, we have not been able to achieve correct full separation of the positive points from the negative points. So, what sort of decision surface would we need in this case? Suppose we had a decision surface which looked like this, let us see. suppose we had this decision surface, it can account for most of the pink points, separate most of the pink points of the green point, even though there is one left over. So, we can have the union of these two decision surfaces, or we can only take this decision surface and ignore the smaller decision surface and treat it as noise. But in order to represent the decision surface, a linear thresholding unit is not good enough. Now, let us have a look at some decision regions. You see, when we have a decision region where all the positive points are in have this sort of shape, that is, all the positive points can be separated by a single line. In those cases, a linear perceptron does work. Problems like the exclusive OR, which we saw in the last class, for this we cannot have a very good, we cannot have a good separation by a linear thresholding unit. There are problems where the regions are meshed. Such problems also we cannot use linear thresholding units. This is another example of a problem where we have two regions and with a hole in a region. So, only this portion is positive and the rest of the region, the green region, this is all negative. So, such problems cannot be separated by a linear unit. And then problems where there is a positive region separated by a negative region, they also cannot be handled effectively by a linear thresholding unit. The Boolean XOR function is one function that we mentioned in the last class, which cannot be represented by a single linear unit. However, if we arrange the linear thresholding units in two layers, in the first layer we compute x1 or x2, in this unit we compute x1 x1 and x2, and here we do an XOR, we can compute an XOR by setting these weights. So, using these two layers of units, we can compute the XOR function. So, we see that if we add a layer to the network, that gives us computing power, and that lets us go beyond linear decision surfaces. So, what we will next study is multi-layered feed-forward network. In multi-layered feed-forward network, we have an input layer where the inputs are fed in. We have an output layer where the outputs go, and within we have hidden layers. These are the other units, these are called the hidden layers, which are not visible at the output and where the inputs also do not fit in. In the hidden layers are the ones where there is no input output, but they help in computing the function at the output. So, if we add a hidden layer, what can we represent? If we add one hidden layer, that is, if we have a two-layer neural network, such a network can represent any Boolean function. Any Boolean function can be represented by a two-layered network. Any continuous differentiable function can be represented by a three-layered network, that is, a network with one output unit and two hidden units. Geometrically, if we have one hidden layer, that is a two-layered neural network having one hidden layer, we are able to separate positive regions that come within a convex hull. Suppose The green region is the negative region, the pink region is the positive region, and the positive region can be enclosed by a convex hull. Such a separation can be learned if we have one hidden layer. Perceptrons, if we use a two-layered neural network comprising a perceptron, they can model such learning problems. However, as we will see, perceptrons are not easy to learn using gradient descent. When we use a thresholding function, because the thresholding function is non-differentiable, we cannot use gradient descent if we are using perceptrons. Today we will look at the sigmoid function, which is differentiable and using which we can learn functions that can be represented by convex hulls. If we have a two-layered network, then we can learn a collection of convex hulls. For example, suppose we have a problem, let me just take a white paper. Suppose we have a problem where, let us say, the positive region is mapped by a number of convex hulls. So, this is the positive region given in pink, and the rest of the regions is negative region given in green. So, such a decision surface can be learned by a neural network having two hidden units. In the first hidden unit, we can learn the individual convex hulls. In the second unit, we can combine them. And therefore, when we use a two-layered neural network, most problems can be represented. In theory, if we add more than two hidden layers, it does not give us any extra representational power. But as we will discuss, merely the fact that a two-layered neural network or a three-layered neural network has a certain expressivity does not mean that the learning problem is simple. Given a learning problem, one has to decide, one has to find out what is the topology, I mean how many layers is needed for solving the problem, and for each layer how many hidden units are needed. After that, the training has to take place, and for training we have to, the training, as we will discuss, when we go for multi-layered neural network, the training does not guarantee that we are able to learn the optimum network. So, the problem remains hard, but a lot of problems have been solved successfully by neural networks. Now, in the last class we discussed linear thresholding units and said that they can represent many types of functions, but they are not trainable by gradient descent. We looked at linear units which are differentiable. Unfortunately, when we want to go for multi-layered neural networks, if we take several linear units together, we do not add to representational power. So, if you add several layers of linear units, what we get is in effect another linear unit, and therefore, it does not have the power to represent all types of decision surfaces. So, the type of functions that we can represent by a multi-layered neural networks using linear units is severely restricted. So, there are other activation functions that we can consider. You see, we do not want to use a linear thresholding unit because it is not differentiable. So, we will try to use functions which are continuous and differentiable, and at the same time which give us representational power. So, two such functions are, number one, the sigmoidal function, represented as y equal to 1 by 1 plus e to the power minus h by p, and the radial function or the Gaussian function, which is given by y equal to 1 by 2 pi sigma e to the power minus h square by 2 sigma square. So, the sigmoidal function and the radial function are examples of two functions which people have used in multilayered neural network. In this class, we will mainly talk about the sigmoidal function. The sigmoidal function has a shape which looks like this. So, as you can see, it is a S-shaped function, but it very closely resembles the step function, with the exception that it is continuous and differentiable. So, it is very similar to the step function. The Gaussian function, on the other hand, gives us a bell-shaped curve, which has been used also in representing neural networks, but we will mainly concentrate on the sigmoidal function in this class. So, this is a sigmoidal function again, y equal to 1 by 1 plus e to the power minus x. The sigma x is the sigmoid function, and if we differentiate sigma x with respect to x, we get, you see, you can do the differentiation, it is an algebraic manipulation, and you will get that d dx of sigma x is nothing but sigma x into 1 minus sigma x, which is actually quite nice. You see, the mathematics becomes much simpler when we deal with sigmoid function, because not only is it differentiable, but differentiating it gives us, we can express it in the form of the function itself. So, the sort of unit that we will use for a neural network, which is called the sigmoid unit, is as follows. There is a summation unit followed by the application of the sigmoid unit. The summation unit computes sigma wi xi, and the sigmoid unit computes sigma of this quantity. So, if net is sigma wi xi, the output is sigma of net, which is 1 by 1 plus e to the power minus net, that is 1 by 1 plus e to the power minus sigma of wi xi. Now, a more general form of the sigmoid function is this: 1 by 1 plus e to the power minus net minus theta by tau. Theta is the threshold. By varying, if theta is equal to 0, the S-shaped function that we get is placed around the origin. If we put theta as some other value, we will be able to give a shift to this function. And tau, 1 by 1 plus e to the power minus net by tau, tau is a sort of stiffness constant. Varying the value of tau, we can vary the slope of the function that we get. For example, if tau is equal to 1, this pink curve shows us the resulting sigmoid function. If tau is equal to 0.1, then we get this white curve, which you see is steeper than the curve with tau equal to 1. So, it more closely, if I make tau less than 1, we get a function which more closely resembles the step function. So, tau controls the slope of the sigmoid function. Smaller the value of tau, higher the slope. Theta controls the horizontal offset of the function in a way similar to the threshold neurons. Sigmoidal neurons can accept any vector of real numbers as inputs and the output a real number between 0 and 1. A network of sigmoidal units with m input neurons and n output neurons realizes a function that maps r to the power m to 0 1 to the power n. Now, let us see how we can train using gradient descent. We have seen that d sigma x dx equal to sigma x into 1 minus sigma x. Now, we will try to derive the gradient descent rule when we have a single layer of sigmoid units. Now, what we will try to do is we will define the error function as we defined in the last class, and we will try to find out the partial derivative of the error function with respect to each value of Wi, and we will try to compute this value, and we will see that that value is equal to minus of sigma over all training instances d, Td minus Od into Od into 1 minus Od into Xi. Td is the target value of a particular, the dth training example. Od is the actual output that we get using the neural network, and Xi is the ith input to which the corresponding weight is Wi. Now, here is the derivation for this. Del E by del Wi, that is the partial derivative of the error function with respect to Wi, is del Wi, and E is written as half Td minus Od whole square, sigma, summation of Td minus Od whole square. So, this is the half of the sum of the square errors. This is the definition of our error function. Now, if we differentiate it with respect to Wi, so first of all we can do some arithmetic manipulation. We can bring half outside the sigma, and we get half sigma del Wi Td minus Od whole square. Then differentiating this, we get 2 into Td minus Od times del Wi Td minus Od. By change of a variable, we get this. Then what is del Wi of Td minus Od? It is minus del Od by del Wi, because Td does not depend on the Wi. Od depends on Wi. How? Because Od is obtained by doing the summation and then the sigmoid. So, what is del? So, we have sigma summation over d Td minus Od into del Od by del Wi. Now, del Od by del Wi we can write using the chain rule as del Od by del net d times del net d by del Wi, and we can simplify this further. Del Od by del net d, what is Od? Od is nothing but sigma net d. So, del of sigma net d by del net d is nothing but Od times 1 minus Od. But that is because this is a sigmoid unit. And what is del net d by del Wi? Net d is nothing but the dot product of W and X, sigma Wi Xi. So, this is net d is W dot X d del Wi. Now, you see that in the W dot X d we have W0 X0, W1 X1, W2 X2. Now, none of these terms depend on Wi except the term Wi Xi. So, this is nothing but Xi for the dth training example. So, ultimately what we get is that the partial derivative of the error function with respect to the weight Wi is minus of sigma over all training examples Td minus Od into 1 minus Od into Xid. So, this is the slope with respect to a particular weight Wi. We can find the partial derivative with respect to all the weights, and we can find the components in all directions of the slope. So, we can compute the slope. Once we compute the slope in gradient descent, what we do is we find the direction opposite the slope, that is we want to climb down. So, we want to find the negative of the slope, and we take a step in that direction. Now, let us see how to train the weights of the network. The basic idea is that we will use a continuous differentiable activation function, which is represented by a sigmoid unit. We will use the idea of gradient descent on the error surface, and we will try to extend this to multiple layers. So, this is a schematic diagram of a multi-layer network with an output layer, input layer and the hidden layer. Same thing here, we have two hidden layers. Now, and we have seen in the that we have been able to derive the gradient descent rule for one sigmoid function, and we have seen that del E by del Wi is minus of sigma over d T d minus O d into O d into 1 minus O d into X I. Now, what if we have multiple layers of sigmoid units? If we have multiple layers, we will use a technique which we call back propagation. Now, we will give the back propagation algorithm, but before we do that, we will try to give you a very simple idea of what is back propagation and how it works. So, the basic idea is that suppose you have some input units here and you have some output here, and then you have some hidden layers here. Now, when do you, let us look at the output unit. When do you change the weights on the different arcs that lead to the output? We only change the weights if the output that we get from the network does not agree with the target output. So, at the output unit, we are able to recognize if there is some error. Error is recognizable at the output unit, and we can try to change the weights of the different arcs that lead to the output unit. We change the weights so that this difference between the target value and the output value is minimized. Now, but if you have a two-layer neural network, how do we know that there is an error at a hidden unit? And how do we update the weight values? Now, only if, because we do not know what is the target value at the hidden unit. At the output, we know what is the target value. At a hidden unit, we do not know what is the target value. And if we do not know what is the target value, we will not know what is the error, and we will have no basis for modifying the weights. So, the basic idea behind back propagation here is that whatever error you observe at the output, you try to allocate the error to the hidden units. If there is no error at the output, that means you can assume that if both outputs there is no error, you assume that there is no error at the hidden units also. But if there is some error here, you try to allocate that error back to the hidden units from which it receives the input. Similarly, if you have an error at this output unit, you allocate this error to the units from which it receives input. So, we propagate the error from the output backwards to the hidden units, and according to the perceived error that in how do we allocate the error? We allocate the error in proportion to the weights, arc weights. So, once we have allocated the error, we know what is the target value that we have to minimize, and therefore, we do gradient descent. So, this is the basic idea of back propagation. Now, let us have a look at the back propagation algorithm. In the first step, we initialize the weights to some small random values. So, we first decide a topology of the neural network which has some arcs, and with each arc there are some weights. We give them small randomly selected values. After that, we feed the training example to the network. For each training example, we take each training example and input it to the network, and we compute the network outputs OK for each output unit K. And then we will do gradient descent with back propagation, and so we are not going to derive the gradient descent for multi-layered neural network. You can refer to a book for that, but it is a little bit the computation is a little bit involved. So, instead of doing the derivation, I will just present the back propagation algorithm. For each output unit K, we compute delta K to be OK into 1 minus OK into Tk minus OK. For each hidden unit H, we compute delta H to be OH times 1 minus OH times sigma WHK delta K. So, you see that each hidden unit takes the burden of sum of the error at each of the output units to which it is connected. So, delta K is what is coming from the kth output unit, and WHK is the weight of the arc connecting this hidden unit with the kth output unit. And then for each, so we compute delta K initially at the output nodes, then at the node above the output node, then at the node above that, and so on. So, after we have computed delta K at all the units, both the output units as well as the hidden units, then we update the network weight as follows. Wij is updated as Wij plus delta Wij, and delta Wij is equal to eta delta j times Xij. So, you see the actual algorithm is quite simple to implement. So, there is an initialization phase. After that, there is a feeding phase where the training examples are fed to the neural networks, and then at each unit starting from the output up towards the input, we compute the value of delta I, and then we modify the network weights, and then we continue if the network is not satisfactory. So, in back propagation, we do gradient descent over the entire network weight vector, and this back propagation can work not only for a neural network with one hidden layer, but to neural network with any number of hidden layers. So, in fact, it can work even though if we do not have layered neural networks, but the neural network is in the form of a acyclic directed graph. We can still do this back propagation algorithm. The basic idea is that we start from the output and then find the delta value at those nodes, and then we find the delta value of those nodes for which downstream all the delta values have been computed. So, backwards we compute the delta values and then we can do the weight training. So, back propagation, as I mentioned, is not an optimum algorithm. By doing back propagation, you cannot guarantee that the weight vector that you arrive at is the best weight vector, but in practice back propagation often works well. In fact, what you can do is, if you run back propagation once with some initial input values and you get a network which does not satisfy you completely, you can run back propagation several times with different weight values, different initial weight values. Now, there are some variations to back propagation that people consider. Apart from the delta term, that is eta delta j xij, some people add another term called the momentum term, alpha delta. So, what is the momentum term? Momentum term takes contribution from the previous value of delta Wij. Why is the momentum term used? You see, sometimes what happens is because there is a local minimum, back propagation, as a result of back propagation, the system may have a tendency to get stuck in the local minimum. So, this is a local minimum, and there is a scope of going further down in the error surface. So, as to prevent your current weight vector to get stuck at the local minimum, what we do is we keep track of what is the previous direction in which the error surface is moving. Now, even if we get stuck in the local minimum, we try to have the momentum of the fall. So, we add to the new delta Wij value, we add the value of the previous slope, so that our ball or our weight function can escape from the local minimum. So, by using the momentum term, we can minimize the error in training examples. Now, so now what we will do is we will study several issues concerning neural networks. For example, we wish to know that suppose we have trained a neural network using our training example, how to find out whether this works well for for unseen training examples. We have to look at that. Secondly, one thing that we have to keep in mind when we use neural networks is that usually neural network training time can be quite high. So, because often training we need about several thousand iterations for the training to converge. However, if we are able to train a neural network, using the neural network is very fast. The feed forward nature neural network, using the neural network is very fast. Now, normally when we use our training examples, which we use for learning, as training time increases, the error reduces, as is shown by this graph. With time, as we train more and more, typically the error reduces. However, as we noted when we looked at decision trees, if we look at new examples which we do not use for training, then with them the error curve may be different. For example, with the new example, usually error reduces for some time and then the error starts increasing, and this, as you know, is due to overfitting. Now, so what we would like to do is being able to detect when the error is at its minimum, and we will like to stop at the point where the error on the test set is minimum. Now, how to detect this point? And as we have done earlier, what we can do is we can have a separate validation set or test set to decide when to stop training the network. Now, suppose we have 3 points. If we have a very simple function connecting these 3 points, often there is a greater chance that such a function can fit unknown examples better. If you have a more complex function fitting the points, such a function may be overfitting the data. Similarly, when we consider artificial neural networks, we have to sometimes we have to look for the simplest neural network that can reasonably fit the data, rather than a very complex topology which is able to fit the data perfectly. So, in a neural network, when we have a too few neurons, that is, if you have too few hidden units, the network may not have enough degrees of freedom to precisely approximate the desired function. But if the network has too many neurons, it will learn the training examples perfectly, but due to this additional degrees of freedom, it may be overfitting the data. So, it may be showing implausible behavior for unknown inputs. So, when we design a neural network, we have to be careful about that. Now, some other problems with neural network is that there are many parameters to be set. We have to decide which, suppose we are using the sigmoid function, we have to decide the threshold of the sigmoid function, we have to decide eta, which is the learning rate, we have to decide alpha, the term associated with the momentum, we have to decide the number of hidden units, we have to decide the number of hidden layers, and so on. So, in a neural network, using a neural network takes a lot of time, as you have to experiment with all these and try to find a good network to fit your data. And coupled with this is a long training time. For each configuration that you take, you have to train it, and training time is typically quite long. So, what are the design steps for an artificial neural network? First, you have to set the architecture for the neural network. That is, you have the number of inputs and the outputs, so to decide which input features to take, how many outputs to take, number of hidden layers that you have, the number of neurons that you will have in each hidden layer. Then you have to run your gradient descent or other algorithms to optimize the weight vector values. And finally, you test the network, and if there is success, if the network is satisfactory, you are done. If the network is not satisfactory, you have to go back to the previous steps, so that you try with different values of the parameters and maybe even different topology. So, there is a lot of parameters that you have to decide when you are working with a neural network. And as we said, that overfitting can usually occur. When do you terminate training? So, normally you stop if the error fails to improve, or you stop if the rate of improvement drops below a certain level, or you stop if the error reaches an acceptable level, or you stop when a certain number of epochs have passed. So, with this we stop today's lecture. We will continue again in the next class. Thank you.